Hi, and welcome to Allen High School's discussion of states of matter and solutions at the APIB chemistry level. Now, we're going to simply be cleaning up a few topics here. We've covered quite a few of these concepts in earlier chapters, and so your notes had a whole bunch of topics that I'm assuming you know already, and I'm going to give you a list of videos from pre-AP chemistry and that we covered earlier in the year to help you with those. So we're going to jump right into the new topics. We've used the ideal gas law quite a bit this year. PV is equal to nRT. Well, not all gases are ideal. An ideal gas is one that follows kinetic molecular theory. That's listed at the beginning of your review portion of these notes. And there are 5 premises of kinetic molecular theory. And most of them are pretty reasonable, especially at high temperature and low pressure. Well, sometimes, based on the nature of the gas or maybe the temperature and pressure, this doesn't fit very well. And so we need some new mathematics to explain what's going on. And there are many mathematical models that are used. This just gives you a glimpse of what it's like. And van der Waals did this a long time ago. And he said, hey, we better correct for 2 key things that we know are likely to be violated. One is the realization that, you know what, gases do have intermolecular forces, either by nature of their structure or because the temperature gets low enough or the pressure gets high enough that the intermolecular forces start to be experienced more distinctly. And as we get to large molecules, they also have a molecular volume associated with them. Remember, kinetic molecular theory says that there is no molecular volume for the gas relative to the size of the container. In other words, the gas is so small that we can neglect its contribution. Well, that's not really the case for the most part. And that's what van der Waals' equation is correcting for. So you take the observed pressure and the container volume and we correct them. And N is still moles and volume. The key factors here are A, this factor A, they're experimentally determined. You have a list of those. That factor A corrects for intermolecular forces. And you should know that. Van der Waals' equation is given on your formula chart, but you should know that the factor A corrects for intermolecular forces. And you notice as you get to molecules that have strong intermolecular forces, like the hydrogen bonding in water or the high London dispersion in carbon tetrachloride, London dispersion, there's a lot of electrons, a high polarizability, strong London dispersion there. You notice that A factor gets fairly large. Now, most likely it's the intermolecular forces that are going to cause a gas to start behaving in a non-ideal fashion. And this is very important in industry, like the semiconductor industry. They had to calculate such things. Okay, correction for molecular volume, moles of gas. Hopefully the more you realize the more moles of gas you have, the greater the correction will be. And that's given by this factor B. So B corrects for molecular volume. And so again, you notice that carbon tetrachloride, that large molecule with a high polarizability and strong London dispersion, also has a fairly significant correction factor for molecular volume. Now, you're not going to have to do any calculations with the van der Waals equation. You have to simply understand it conceptually, which can be a little harder. Y'all are pretty good if I give you a formula and say plug and chug. This is about understanding that if molecules are attracted to one another, then the pressure is going to be altered. So that type of thing. All right. Now, the other thing that is new in terms of gas laws, we used to be able to do this at the pre-AP level, but we've lost quite a few days for a variety of reasons and had to get rid of it. And that's Graham's law. Graham's law primarily discusses effusion. And mathematically, it models effusion very well. It's an estimate for diffusion because diffusion is movement of one gas through another gas. And so the presence of that other gas can complicate the mathematics. But it can be a good estimate for that. And it works fairly well for effusion. And it goes all the way back to kinetic energy being equal to 1/2 mass times velocity squared. Okay? And we take some ratio of these and convert mass into molar mass, and voila, we end up with these ratios. And you notice that the rates are inversely proportional. In other words, as you increase the size of the molecule, you're going to decrease its rate. Hopefully that's pretty reasonable. Well, if you decrease the rate, it's going to take more time. So you notice that time is directly proportional to molar mass. Now, when I do these, I don't memorize the formula. I kind of build the formula, and I think you'll see that as I get going here. Okay, this question says rank these according to the rate of effusion. Now, it doesn't say increasing or decreasing, so you're going to have to be very clear whether using greater than or equal to signs. Now, this has to do with molar mass, so we simply look up the molar masses. Neon is 20.8 grams per mole. CH4 is 16.05 grams per mole. Hopefully you can guess that SF6 is a big old substance, but we can get it into the gas phase. You'd be surprised what you can get into the gas phase at the right temperature and pressure. When I was in the semiconductor industry, I was floored that they take a salt like silver chloride and you can get that into the gas phase. All right? So these are the molar masses. So now we want to rank them. If you increase the molar mass, remember you decrease your rate of effusion. So the smallest is the fastest. CH4 is greater than neon, is greater than CO2, is greater than SF6. So that would be one way that this can be discussed. Now let's take a look at the next one. It says oxygen gas effuses at a rate 2.23 times faster than an unknown gas. Man, reddish brown gas, I'm going to guess it's got nitrogen in it, but we're not really told. So, all right, so let's write that mathematically. The rate, sorry I put velocity, it's an old habit. Let's put the rate. Velocity works too. Rate of O2 is equal to 2.23 times the rate of our unknown gas X. And then it says determine the molar mass. Well, when I build this, I like to put my unknown in the numerator. So I'm going to put my molar mass of gas X on top. That means my molar mass of oxygen is in the denominator. Add that square root. Now remember, rates are inversely proportional. So that means the rate of O2 will be on top and the rate of X will be in the denominator. Now, what I'm going to do is substitute in here. In place of the rate of O2, I'm going to put that equality in there. So I'm going to put 2.23 rate of my unknown X over rate of X is equal to the square root of my molar mass. You know, a lot of people just use a single M for molar mass, but I like to use the double one because otherwise it looks to me like it's too much like molarity. Okay, I know oxygen. I'm going to go ahead and throw that in there. Okay. Now, do you notice once we put in the relationship between these two rates, that cancels? So now all I have to do is to get rid of the square root, I'm going to square this side on the left, and then I'm going to multiply by 32, and that's going to equal my molar mass of X. And when I did that algebra, assuming I did that right, you always want to check me, I get 159 grams per mole. Man, can't imagine. That's a pretty big molecule to be a gas, but we're going to run with it. Okay? So that's one way. You notice I built my equation, so my unknown is on top, and then I used the relationship that rates and masses are inversely proportional and worked it from there. Now, this time, I'm not asked for a specific rate. I'm asked for a relative rate. So I have my rate of NO2 over my rate of N2O5 is going to equal a factor. Well, let's build our formula. Molar masses are inversely proportional. So the molar mass of NO2 is going to go into the denominator so that it's an inverse proportionality. And then my rate of my molar mass, of N2O5 goes in the numerator so that they're opposite. Let me clean that up. Sorry about that. Got distracted by checking my time. Okay, so now I can get that because it's easy to get those two molar masses. This is 108.01 for N2O5 and 46.005. I have on my iPhone, I have a little app that calculates molar masses for me. So if you want to see that, let me know, because it's actually kind of nice to just plug in a formula and have it chug out my molar mass for me. You can't use it on a test, but it's nice when you're doing your homework. Again, if I did my algebra right, I get 1.532. So you can leave it at that. That's 1.532 to 1. So that is my relative. But another way I could write that is that my rate of NO2 is 1.532 times my rate of N2O5. And hopefully that makes sense. The smaller molecule is faster, 1.5 times faster than my larger molecule. So let's take a look. Let's go on from here. Hopefully you're getting that one. That's one of our topics. Now, that was the new learning on gas laws. I'm assuming you know all the rest, and I'll give you videos if that's a bad assumption, or certainly I'm always available to help you if you need some help on that. Now I'm going to go into the new learning for solutions. We've already done molarity, molality, mole fraction, colligative. The two colligative properties we did is we did freezing point depression and we did boiling point elevation. I just made videos for that for pre-AP, plus you have your earlier videos from like Unit 2, Unit 1 or 2, Tools of the Trade, that we did at the very beginning of the year to review that. I'm going to go into a couple of others of the colligative properties and gas dissolution. So let's take a look at this new formula. We have here a formula that talks about the solubility of a gas. We did solubilities of insoluble salts as KSP. As part of our review, I put in some solubility graphs, and you have that available. Now we're going to delve in just a teeny bit more into solubility of gases in a solution. So this shows a gas. This would be a low pressure. And you notice that as we increase the pressure, more gas molecules will dissolve. I don't know why I put a B there. As we increase our pressure, we are going to increase the solubility of our gases. And that's given, that's our solubility of our gas. It's given by a constant that is experimentally determined, because you notice here, this is with temperature, but you notice that at any given pressure, the graphs are very different from one another. And the solubilities are different. The solubility is going to depend on things like intermolecular forces and attractions and that type of thing. So these are experimentally determined. This is called Henry's constant, and that's capital M is for molarity, and this is millimeters of mercury. So we're going to need to use torr, or that's the same thing as a torr, right? Or millimeters of mercury for this. So here it says, what is the concentration? That's just another way of saying what is the solubility. In a freshwater stream, oxygen dissolved in water is a very important concept in aquatics, and in fact I have an oxygen sensor that will help us determine that. We have 25 degrees Celsius and 1 atmosphere, and it gives us the mole fraction. That's because we need the partial pressure of oxygen in the air that's 1 atmosphere. Well, man, that gets us back to Dalton's. So the first thing we're going to do is use Dalton's law of partial pressure that says that the partial pressure of oxygen is going to equal the mole fraction of oxygen times the pressure total. That's one of the forms of Dalton's law that we saw. Pressure total is the sum of the individual pressures, but this is another way to find an individual pressure. So the problem made it very easy on us because it was 1 atmosphere. And that gives us 0.21 atmospheres is the partial pressure of oxygen. Well, we have to have torr because our Henry's law constant is in torr. So I'm going to multiply that by 760 torr per 1 atmosphere. And then I'm going to plug it into my solution, into my problem for my solubility. S is 1.66 times 10 to the minus 6th. That's my Henry's law constant for oxygen. That pressure, when I calculated it, is 159.6. Now, remember, this is molarity per torr, and this is torr. So we're going to end up in a solubility that's in molarity, 2.6 times 10 to the minus 4th molar. Now, the question said to answer it in grams per mole. And so we simply have to do one more conversion factor, 2.6 times 10 to the minus 4th moles per 1 liter. That's what molarity is. Mass to moles, use molar mass. So that's 32 grams for oxygen. And I think I'm missing something on my calculation here. I have 8.5 grams of oxygen per liter, but I believe that that's got to be, I think I'm missing my exponent there. So let's take a look. Sorry, this is going to take me a second. 2.6 times 10 to the minus 4th times 32 gives me 0.0085 is what I'm getting. So 0.00832 grams per liter. So hopefully you will double check my algebra there, but I think that's pretty good there. Sorry about that. All right, we're going to move into solutions, some more new learning. So until the next video, this is signing off.